Okay, so we talked about the different fuel cell technologies. How does the deployment work? So the addition, so you're carrying the same figure now with this central fuel cell gas turbine hybrid production, with the users being the industry, commercial, and residential members, and hydro and nuclear are part of the grid as well, part of the energy portfolio, as well as renewables. And we have storage to manage intermittency and so on. Tiger is the addition here. It's called Transmission Integrated Grid Energy Resource. Okay, so this supports local grid constraints. So that's another way of managing different customers here. So instead of going from the central grid to different users, it's got an intermediate transmission integrated grid energy resource, which provides what are referred to as ancillary services of monitoring the load, cranking up and cranking down the production based on the demand, etc. Plus, there is also this addition of, we already saw, deployment of fuel cells at local level. So here the industry has a fuel cell in place fuel cell, unlike based on moving vehicles and so on, and so do these, but the residents here are not shown. Residents have solar and not wind, as we talked about the various issues. Plus there is a biogas related fuel cells. You can see the signs are all fuel cell here. So where are these deployments actually occurring? If you look again at the fuel cell sites in California as of 2019, there are quite a number of them in the northern and southern California. Obviously it's a big state, so these look like a large number, but obviously the penetration of fuel cell technology into the state system is not there yet in terms of accomplishing 100% renewable energy portfolio, right? Fuel cell market growth rate by region, projecting over to 2025. The Asian regions and Australia show very high growth rate, but they are also starting out late. It's quite medium in much of Europe and over Russia and Eastern Europe as well, and quite low over here in the Western Hemisphere. Why is that? Well, this is just what the Mordor Intelligence Research says. We have to figure out why that is and what are the levers in the system that would change this dynamic. Africa is understandable because it's still developing. Maybe Middle East is understandable because it's still looking forward to burning its oil, selling its oil, and so on. But solar is already big in the Middle East because they have so much sun and so many sunny days. Okay. Coming back to the two pathways of how to manage the management of the electricity production and distribution. The two pathways differ in the management of load balancing, reliability, and dynamics associated with the intermittency of the renewables and limited capacity factors. Remember, the actual production divided by the maximum potential that accompany high penetration of solar and wind power generation. So if solar and wind become a bigger and bigger part of the portfolio, either at a state level or like California, or at the national level, then the two pathways do not agree on how to do this, and they also differ in the uncertainty in forecasting the intermittency of solar and wind resources. In the climate science, there are some efforts in the weather and what are called extended range forecasts. So you have 1 to 3 days weather forecasts and 3 to 10 days. They are called short and medium range forecasts. And then you have what is called extended range, which goes from weeks 2 to 4. That's called intra-seasonal or sub-seasonal forecast. And then there is a seasonal to interannual forecast like El Nino and monsoon and so on. So the use of these forecasts to look at wind is quite extensive already, but also there are efforts to forecast number of degree days which put a load on the grid, and number of sunny days, and so on and so forth. So the uncertainty in forecasting the intermittency is not dealt with in the same way by the two pathways that we looked at. But both of them agree that storage will be required to deal with this uncertainty. But they then again differ on how to manage this storage in terms of the amount and types of energy storage, whether to rely just on electrical batteries and pumped hydro. Remember, you pump water up the hill and then let it flow down and drive the turbine. Which puts challenges on making sure of carbon neutrality and emissions reductions, and the need for a clean, firm 24/7 power generator in addition to solar and wind power generation. So there's a difference in the storage and in the baseline production system itself. Okay, so the pathway 1 shown here from this section in 100% renewable grid, both of them agree on the need for 100% renewable grid. In pathway 1, use of the lithium-ion and pumped hydros to store energy during low loads. So when the demand is low on the grid, instead of curtailing production, you use the capacity that exists to load charge lithium-ion batteries, and you pump up the water and create pumped hydro capacity to be used when the load goes back up. So that's what we looked at. Here is the central generation fuel and gas turbine hybrid production. Renewables are there, hydro nuclear are there. Storage originally we thought about are still there. And then we have the transmission integrated system, Tiger we call here. And distributed generation is still part of the system with lithium-ion batteries in the transmission system. Remember, Tiger is transmission integrated grid energy resource. So you have storage and the capacity to pump up power generation through the lithium-ion batteries when load goes back up, and the pumped hydro. In pathway 2, on the other hand, energy systems analysis is used to evaluate many scenarios. So you take any season, you take the users on the grid, and you project into the future for a few days, a few weeks, whatever the system of software allows. And hydrogen batteries resources created, and 24/7 load following clean energy source is also argued to be needed. So those are the big differences that we discussed. So again, look at the figure carefully and keep comparing them. You have still central generation and distributed generation. We have the lithium-ion batteries in the system, but now you have here electrolysis system. So you can see the little change in the colors. They look exactly the same, except here it is this bluish greenish color and the bluish dark color on this side, whereas this one has it reversed. So these are electrolysis to create through, let's say, SMR, the steam driven methane regeneration, where you have extracted hydrogen. So you have hydrogen storage, which is piped in to various locations to drive fuel cells to augment the distribution of power. Okay, so here you don't have that. You're just relying on Tiger stations and lithium ion or a pumped hydro storage system, whereas here it argues for a 24/7 load following clean energy source, which is going to be accomplished through this use of excess load during low load times to produce hydrogen and store it and pipe it into the grid to make it locally available. So you still have Tiger stations, distributed generation, and so on. So I don't know if you really want these kind of details at this stage, but at least be aware that there are differences in the way it's being thought about. Both are driving towards 100% renewable energy. Both are relying on new technologies and batteries and storage and renewable power, central production with distributed production, but there are subtle differences in the way the two do the details.